as we can. Might lecture a little bit in lab because today's lab is pretty short. It's just a smelly lab though, so it's nothing to turn in for the lab, but it's good. Some of them are good smells. You guys are gonna be synthesizing esters and stuff today, which is a class of functional groups for organic molecules. The esters can smell like bananas and stuff too, so they smell good sometimes. Sometimes they don't smell good. But it's also, you use acetic acid. Does anyone know what acetic acid is? It's not familiar. It's because I always give it to you for the equilibrium problems. Acetic acid and acetate, but acetic acid is vinegar, so your initial starting compound is vinegar, which is not that pleasant smelling. So, okay, so organic chemistry. Does anyone know what the organic chemistry is, or how do we define organic chemistry? What do you guys think of when you think of organic? Carbon, right? So this is what organic chemistry is. It's a chemistry of carbon-based molecules, right? And so what's so special about carbon? Well, carbon forms up to 4 bonds. And like I mentioned before, it can have 3 different hybridizations, right? Carbon can be sp, sp2, and sp3. And it forms 4 very stable bonds, generally. It can form bonds with itself, with other atoms, and it forms covalent bonds with those, right? And the ability for carbon to hybridize like this gives it its geometry, so it can adopt a number of different geometries, trigonoplanar, tetrahedral, linear geometries. That allows it to make many different shapes in 3-dimensional space. Right? So double and triple bonds can form between carbon atoms because if you don't hybridize all of the p orbitals, right? So when we talked about hybridization before, we said an s plus a p gives us 2 sp orbitals, right? But what's left over with the other 2 p orbitals that you have? And so the leftover p orbitals that don't get hybridized, those become unhybridized p orbitals. Our sp orbitals are involved in the single bond, or what we call the sigma bonds between carbon atoms. And the unhybridized p orbitals, when we fill electrons in those can form what we call pi bonds, which are double and triple bonds, right? So depending on the number of unhybridized p orbitals, we get overlap between the unhybridized p orbitals, right? So these are the unhybridized. I'll do a different color. These are unhybridized p orbitals. And those form a chemical bond the same way to sp orbitals overlapping do. Unhybridized p orbitals overlapping if they have the same parity, electron density, then they can form another bond with each other. So this is the mechanism by which carbon forms double and triple bonds. So this would be a double bond, what I have drawn here, but if we also have overlap between the 2 perpendicular orbitals, so that would be these 2 right here, these bonds are called pi bonds. Right, those are what allow double and triple bonds to occur. Right, so this would be an sp hybridized carbon because we have 1 hybridized or 2 hybridized sp orbitals and then 2 unhybridized p orbitals. Right, I only have 1 sp orbital drawn here, but we also have another one that goes in the other direction. So the sigma bonds are how we form the single bonds with other carbons and other atoms. The unhybridized p orbitals is how we form double and triple bonds. Right? And you can imagine now, if you have a double bond or a triple bond, because these are, we say, orthogonal or perpendicular to the direction of the single bond, that it's like adding extra ropes between 2 wooden rods. Now that restricts the movement a lot because the ropes won't let you spin and twist around. So these pi bonds restrict the movement of this bond. It can no longer rotate. And because it can no longer rotate, that restricts the geometry of this. So introduction of double and triple bonds into a carbon structure will determine the overall shape of a molecule. That's why proteins have very specific shapes, because the backbone is largely made of carbon and nitrogen atoms that restrict the movement and the shape and function of proteins and polymers are very intimately related, right? If you deform a protein or denature a protein, it stops to function anymore, right? So that is where the geometry comes from. It comes from this bonding nature of carbon. And carbon can also do what's called catenation, which just means it can form polymers, right? So carbon can bond to itself to form polymers. Does anyone know what a polymer is? So a polymer is just a repeat unit of things that are bonded to each other. Repeat unit bonded to each other. So what that means, for example, a very simple polymer would be polymethane or polyethane, which is just carbon. It'd be a chain of carbon atoms. And it goes on. These are usually very large. The squiggly line just means that it keeps going on and on of carbon atoms, and then we'll make this a hydrocarbon, so it's all just bonded to hydrogens here. Right, so this is the repeat unit is just CH2, and you have a bunch of CH2s that are just bonded to each other. That's what it means for it to make a polymer, right? It's a repeat unit bonded to each other. And carbon isn't the only atom that can do this. There are other types of polymers as well, and polymers can get pretty complicated. Most of your biological molecules are biological polymers. They're very long chains of either carbon or, if you look at DNA or RNA, you have your phosphate carbon backbone, so phosphorus and oxygen is part of that backbone as well. Right, but carbon, because of its variable bonding nature, likes to form 4 bonds, it can hybridize in multiple ways, has a very good propensity to catenate or form polymers. And that's what makes it so kind of ubiquitous in life, because life is derived from polymers. And so when you look at polymerization reactions, you're looking at reactions of taking a monomer, which is a single unit of a polymer, and just adding them on to the chain, right? That's how these processes, how you synthesize a polymer. You take a bunch of individual CH2 or CH3, CH4 molecules, and then they get added onto the chain to form the polymer. All right, so this is kind of the basis, and the first probably 4 weeks of organic chemistry, you'll spend a lot of time looking at the bonding nature of carbon and the hybridization, how it hybridizes. So the first class of functional groups for organic molecules are just hydrocarbons, right? And hydrocarbons are just compounds made of entirely hydrogen and carbon. You're like, well, why are there so many classes for compounds that are only made out of hydrogen and carbon? Well, because the different bonding nature of carbon allows for different variations in functional groups, even just within these 2 atoms. So alkanes are going to be hydrocarbons with only single bonds. So an example, if we have this is ethane, is we have a carbon bonded to another carbon and only hydrogen. There's no double bonds or anything in the structure. Another way of saying that is only sp3 hybridized carbons, right? If you have 4 single bonds, that means you have an sp3 hybridized carbon. Why? Because you don't have any double bonds. You have no unhybridized p orbitals in this structure. So those are what our alkanes are. Alkenes are hydrocarbons with at least 1 double bond. So for example, if we look at the same molecule, but now we've added a double bond, removed a hydrogen, right? Now we have a double bond between these 2 carbons. This is considered an alkene, right? And an alkene has a very different chemical properties, physical properties compared to alkanes. So when we talk about saturated versus unsaturated fatty acids, right? Those have very different melting points, very different interactions with your body, right? So the unsaturated ones tend to not be as healthy. They can form plaque and stuff in your arteries. And so those are usually, the only difference between those two is they can have the exact same number of carbons, the exact same number of oxygens, exact same number of hydrogens, but just there's a double bond introduced into the long carbon chain. And that single double bond drastically changes the property. Right, so this class of molecules are called alkenes. What do you guys think an alkyne is?
At least one triple bond.
Yep, at least one triple bond. Right, and so we have an alkyne with 2 carbons, that's what this will look like. And we see that both of these carbons have 3 bonding partners, 3 zero lone pairs, trigonal planar. Trigonal planar means we have 1 unhybridized p orbital, that's what creates the double bond, that's why that's an sp2 hybridized carbon. So you have at least 2 sp2 hybridized carbons in an alkene. An alkyne, right, we have 2 unhybridized p orbitals, one in the z direction, one in the y direction, and that allows us to form 2 pi bonds. That means that we have at least 2 sp hybridized carbons in that structure, right? And if we look at the geometries, this is like a tetrahedron, this is a trigonal planar carbon, and this is linear right there. And the last class of hydrocarbons are aromatic hydrocarbons. And these are more based off of their properties than any specific structure. And what happens is you can get electron delocalization. Does anyone know what I mean when I say electron delocalization? Has anyone heard the term sea of electrons for metals? Oh, really? That's what everyone says when they talk about metals for the first time. Well, so the reason metals conduct electricity is because they have a conduction band where all the valence electrons for all the metals exist. And they say it's a sea of electrons, meaning these electrons just kind of flow through the metal. They're not bound tightly to the metal itself. And so when you put an electrical current or a voltage difference across the wire, it causes those sea of electrons to move, right? So that's called delocalization of the electrons. What that means, right, so you probably hear, local versus non-local and physics talks and things like that, and it sounds really confusing. All that means is that the electron is not localized onto an atom, right? It's hopping around from atom to atom. It's delocalized, spread out over the entire, conducting surface of whatever that metal is. And so with organic compounds, you can have similar properties if you have a couple things, right? So they're usually planar molecules with conjugated pi bonds. So a very common organic molecule is benzene, and you guys will see plenty of this. Hopefully not smell too much of it, because it's carcinogen, but I'm sure you will smell a lot of it. This is what I said. I said it when I was done with my second semester organic chemistry that I'm tired of huffing benzene, so I'm never going to work in a lab again, and now teaching chemistry and huffing benzene, especially when I teach OChem. Carcinogens, not that good, very good solvent, and it's an aromatic compound. So what a conjugated pi bonds mean, conjugated just means alternating pi bonds, right? So if we look at the structure right here, we have double bond, single bond, right? Double, single, double, single, double, right? So we have an alternating or a conjugated pi system. And if the molecule is planar, what happens is the electrons that are in these pi bonds, right? All of these carbons, right? They're all involved in at least one double bond, which means they're all sp2. So they all have these unhybridized p orbitals that are coming in and out of the board, right? That are coming in and out, and that's where the pi bonds are formed. So all of them are hybridized like that. So the reality is that this structure is the same thing as if we just switched the location of the pi bonds. C, like that. And then I'm not going to draw the hydrogens, but the hydrogens are there, right? So all I did is I just swapped this bond down here, that one up there, and that one there. And because these bonds can swap with each other, it means that these electrons are actually not localized in this specific pi bond, for example. It's not localized in that pi bond. It can delocalize to the pi bond that's next or adjacent to it. And because that one can delocalize to the one that's adjacent to that, these electrons are actually all delocalized over the surface of this molecule. And what that does is it makes the molecule extremely stable. So the molecule is extremely stable, and it adds this extra level of stability, and it makes it very inert, right? So it's a good solvent because it's very inert, doesn't react. It's kind of hard to get benzene to react. And they usually, the name actually comes from the fact that aromatic molecules, what do you think the name might come from? What do you think when you think of aromatic? Smelling, right? So the aromatic molecules tend to be very smelly. That's why I said I was huffing benzene. It doesn't smell, I mean, it doesn't smell bad, but it doesn't smell that great. But it has a strong odor, right? So aromatic molecules tend to have a strong odor. But the aromatic comes from this conjugated system with delocalization of electrons that leads to this property of stability. That's how we define what an aromatic molecule is. And so just with carbon and hydrogen, you can have already 4 different classes of organic molecules. Now when you start adding oxygen and nitrogen, which are the other important atoms for, and sulfur, phosphorus, other important atoms for biology, now you can see that there's a lot of functional groups you're gonna have to remember in inorganic chemistry. All right, so these are the ones that you'll be most focused on, especially in the first semester of organic chemistry, and then maybe a little bit of alcohols too. And so when we draw hydrocarbons, you know, you could see I didn't like to draw all the carbon atoms and all the bonds there. There's 3 different ways we usually represent organic compounds. The carbon skeleton is usually the one I'll be going with after introducing it because it's a lot easier to draw a carbon skeleton than the full structural formula. The full structural formula is all bonds and atoms are drawn. So example, when I had ethane, this is the structural formula. It's just the Lewis structure of the compound, right? This is just the Lewis structure. The condensed formula is when we ignore vertical bonds, and depending on where you look and which textbook you look at, sometimes you ignore the horizontal bonds too. And so I'll put horizontal as well. So for example, this becomes, for the condensed formula, CH3, CH3 if we're not ignoring horizontal bonds, or it can be CH3, CH3. All right, so this represents this molecule. And then the carbon skeleton is my favorite and will be your favorite too, is carbon atoms are kinks in a line or edges, and hydrogens are not drawn. Right, so whenever you see a bend in a line, that means there's a carbon atom there. If you reach the edge of a line, that's a carbon atom there. And then you just ignore the hydrogens. And the reason for that is because for organic molecules, if you have, let's say, 3 bonds to that carbon, to a fluorine, and to 2 other carbons maybe, you just assume that the hydrogen takes the last spot. Carbon always needs to satisfy the octet rule, and it always will have hydrogens bonded to it. Especially for hydrocarbons, you know, all the spots are filled with hydrogen. So what these two ethane molecule looks like, what the ethane molecule looks like in the carbon skeleton, is just like that. It's just a line, right? Here, carbon atom 1, carbon atom 2, and the hydrogens are just implied, right? So those are the carbon atoms, and you're just saying, okay, well, this carbon is only bonded to one other carbon, which means that it has, and there's no double bonds drawn here, right? The bonds are explicitly drawn between carbons, which means that this has 3 more bonds to it for it to satisfy octet. Those 3 more bonds have to be to hydrogen. That's what the assumption is with the carbon skeleton. All right, so let's do an example. So we have butane, right? Butane, we have 4 carbon atoms. So the structural formula is going to be 4 carbons, and then because it's a hydrocarbon, all the other spots are filled with what? Hydrogen, right? So H, 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 H. And this is a relatively small alkane, right? Because it's only single bonds. It's a relatively small alkane, and you can already see this starts to get very annoying to draw, right? I'm tired of drawing all the bonds to all the hydrogens, which is why I don't like to draw the structural formula. But this is just a Lewis structure. There's no lone pairs on hydrogen, so all the lines are just drawn. All right. For the condensed formula, am I okay to move on? The 2 ways that you might see it is you'll see CH3, CH2, CH2, CH3, right? That's just all the vertical and bonds to hydrogen that are ignored. Or you might see it CH3, CH2, CH2, CH3, right? Both of those you might see for a condensed formula. This one just ignores the vertical bonds, and that one ignores only the horizontal. Sorry, this one ignores the horizontal bonds and vertical. This one just ignores the vertical bonds. And so then the carbon skeleton, which will be the easiest to draw, is 1, 2, 3, right? We have 1, 2, 3, 4 carbons, right? So we have all the carbons we need, and the rest are just filled in with hydrogen, right? So the carbon skeleton is the easiest to draw. So now you know when you're looking at chemistry and you see all those hexagons and triangles and stuff, that's actually just representing a carbon molecule. Because carbon can form chains, it can form cyclic molecules that form rings, and the long polymers. But this is what those lines represent. They just represent carbon atoms and hydrogens. All right, any questions on the different formulas, the structural, condensed, or the carbon skeleton? So unless it's explicitly asking for the structural formula, I'm always okay with you drawing the carbon skeleton, and I'll probably be drawing mostly the carbon skeleton as well. All right. So then, the real fun in organic chemistry, and probably every exam will have a section on this in your class, is the naming of all of these different carbon functional groups, carbon-based functional groups. And even just for hydrocarbons, the naming has its own naming structure. So these are saturated hydrocarbons, meaning that there are no, there's a couple different ways to phrase this. There's no double or triple bonds, or all sp3 hybridized carbons, all tetrahedral carbons. And so the naming for alkane is we have a prefix that identifies the number of carbons in the longest chain, right? Prefix to identify the number of carbons in the longest, and I'm going to put longest first, and then in parentheses I'm going to put the highest priority chain. The reason I put that is because sometimes you don't just go based off the longest chain, but also the one that has the highest priority functional groups, which we'll talk about later. And so the prefixes, because we don't want to make anything easy, are different from all the other prefixes that you've looked at before. The prefixes for carbon-based molecules for the longest chain, based off of the number of carbons in that chain, we have a prefix. And if we have 1, 2, 3, 4, 5, 6, 7, 8, continued, 9 and 10, the prefix for 1 carbon is meth, the prefix for 2 is eth, the prefix for 3 is prop, prefix for 4 is bute, 5 pent, that one's nice, 6 hex, that one's also nice, 7 hept, oct for 8, and then 9 is known, and then 10 is dec. Alright, so you have a number in your longest chain that's associated with the number of carbons. Right, so when we looked at the previous example, there was 4 carbons in it. It was called butane, right? Because there's 4 carbons in that molecule, so bute is the prefix there. And so, once you have the prefix, the suffix for this carbon-based molecule, the suffix, I'll go back in a second, the suffix is ane for alkanes. So just ANE. So butane only has single bonds in it, so it's an alkane. Bute for 4 carbons, ane to say there's only single bonds in it. So the suffix is ane. So for example, if I draw this molecule, 1, 2, 3, 4, 5, 6, how many carbons are in this molecule? 6, right? So this is 1, 2, 3, 4, 5, 6. We have 6 carbons, so the prefix should be what? Hex. Are there any double or triple bonds in this molecule? Nope, so what should the suffix be? Ane, right? There's no double or triple, so it's ane, right? This is only single bonds, and this is because there's 6 carbons. Do I have an extra slide for? All right, and then we can also have, because carbon, I said, can also form ring structures. For a chain structure, we use the naming convention that we just said, or the rules. If it's a cyclic molecule, you just start with cyclo before the prefix. All right, so this is like a prefix to the prefix to indicate that it's a cyclic molecule. So for example, if we have this molecule right here, how many carbons are in that molecule? 6, right? Because we count each bend or kink in the line, that represents a carbon atom. So we have 1, 2, 3, 4, 5, 6. So the prefix, we add cyclo because it's cyclic molecule, meaning it forms a closed loop, right? Cyclic means forms a closed loop. There's 6 carbons, so we put hex, and are there any double or triple bonds? Nope, so that becomes ane. Organization, reactions, functional group, degree. We can also have, actually I'll talk about that on the next one, right? So that's how we name an alkane. In this naming convention, even if we add other functional groups, we'll continue throughout throughout your studies in organic chemistry, right? So the prefixes are gonna be the same for any functional group. That tells you how many carbons are part of the longest chain. The suffix for this will actually change though, depending if it's an alcohol, right? So if you've heard of the term ethanol, right, that's an ethane molecule that has an alcohol group, so it becomes ethanol. You add an OL to it. Okay. So for alkanes, we can also have group-based naming versus the main chain naming, right? I said the longest possible chain. So you can also have substituent groups on organic molecules. What that means is if I have something like this, and I include this line here, right? The longest chain has how many carbons here?
5.
5, right? The longest chain is 1, 2, 3, 4, 5. We have another group here though, which I'm gonna highlight. Right? This is an alkyl group. This is what we call an alkyl group. It's an alkane molecule that's not a part of the longest chain, right? So this is not a part. It's an alkane that's not a part of the longest chain. It's an alkane that is that. Right? And whenever we have a group, the way we indicate this is we put the number carbon, the group is on, right? So what number carbon is this alkane group on the main chain? 3, right? So that's on the third carbon. Then you put a dash. Then you put the name of the alkane group. And you subtract the ANE ending, and then you add the YL ending. That indicates that alkyl group, right? That's where alkyl comes from. It's not an alkane, it's an alkyl group. That this carbon group is not a part of the longest chain. It's a substituent group on the parent chain or the main chain of the molecule, right? So how many carbons are in that group?
5.
In the longest chain, there's 5 carbons, right? So we don't double count the carbons. So how many carbons are in this group here? Right, are there any bends in this line? No, which means that the only one would be the ending carbon right here, right? So there's 1 carbon in this group. So what's the prefix for 1? Does anyone remember?
Oh, wait.
For a single carbon, what would that be? Meth, right? So what we would say is on the third carbon here, we have a methyl group, right? Because there's 1 carbon in that group, so that's a methyl group. After you do the group name, you just add the name of the parent chain. So what that looks like for this molecule is we said that on the third carbon, there is a methyl group, so it's 3-methyl. And then what was the name of the parent chain here?
Pentane?
Yeah, there's 5 carbons, so it's pent. It's only single bonds. So this will be pentane. So 3-methyl indicates that that's an alkyl group on the third carbon. Pentane is the main chain you have in this molecule. If you have, some rules, multiple groups are listed in alphabetical order. right? So if we have an ethyl group and a methyl group, we first list the ethyl group, then we list the methyl group, and we indicate in both of them where they are. And you might ask, well, what if we have multiple of the same group? If you have multiple of the same group, what you're going to do is, let's say we had another methyl group on 4. You put a comma here and separate the 3 and the 4 by a comma, and then dash methyl. And it says on both the 3rd and the 4th carbons you have a methyl group there. Right, so am I good to go on to the next slide, or are we still writing? Are we still writing? So if there's multiple of the same group, separate carbon number by comma. COMMA? It's a weird word. Right, so if we had our pentane molecule, so now on the, let's see, we'll do the 2nd and the 3rd carbon. So we have 1, 2, 3, 4, 5. We now have 2 methyl groups, right? 1 methyl group there, 1 methyl group there. This would be named 2, 3, and then we also add a prefix to the group. So if we have 2, these prefixes are the familiar ones that you're used to for covalent prefixes, for covalent naming prefixes. So what do you guys think 2 would be? It'll be di, so it'll be di for 2. Right, so if we have difluoro, that means you have two fluorines, right? So this will be dimethyl, and then the name of the parent chain, pentane. Right, this is saying that we have 2 methyl groups, 1 on the 2nd and 1 on the 3rd carbon here. And you might also ask yourself, well, how do I know to number the chain from left to right here instead of right to left? So the IUPAC, which is the naming convention for all organic molecules and all chemistry molecules in general, is we always number to give the highest priority groups the lowest possible number. So for example, if we numbered it the other way, so I'll redraw the molecule. Right here, let's say I numbered it 1, 2, 3, 4, 5. The name would have been 3, 4 dimethyl pentane. You would still be able to draw the molecule, but it's not the most accurate name. So depending on your organic professor, they probably would be about this, at least when you're first learning it. Yeah.
Will cyclic molecules also have the alkanes or the alkanes on?
Yeah, so even cyclic molecules can have them. Right, so if we had a molecule, yeah, so let's look at something like that. If we had something like this, let's do this. So we'll do here, and then we'll do something like that. All right, let's see, how would we name a molecule like this, right? How many alkyl groups do we have on this cyclic molecule? 2, right? We have how many in this first group? How many carbons are in that alkyl group?
Would you go from top to bottom or bottom to top?
So then we'll get to the numbering convention in a second, but first we'll just identify. 2 carbons are in that group, and what about in the other substituent group? 3, right? We have 1, 2, 3. So we have a ethyl group for 2 carbons and a butyl group for 3 carbons. And now we say, okay, I'm going to start numbering this cyclic molecule, how am I gonna number it? Well, I always wanna put the substituent groups on the lowest possible number, right? So where do you guys think I should start?
Would it be top to the right? Like,
Yeah, you could start top to the right, and this is where, professors can get really nitpicky. The most accurate way to do it would be 1, 2, 3, 4, 5, 6. Right? Why do we do it this way? Well, this puts
oh, you can
that,
swing it
yeah,
up
you
on
can,
top.
you're in a cyclic molecule, arbitrary number, which one's gonna put your highest priority group on the lowest possible number. In this case, actually technically I'd start here and go the opposite, because technically you put them in alphabetical order, but
So it'd be the B first.
I'm not gonna grade you guys on that, but the most correct way would probably be to number it. This one, because B goes first, it has a slightly higher priority. It'll be 1, 2, 3, 4, 5, 6, right? So you can number it in either direction. And then the name for this one will have 1 butyl. When we have multiple groups on different numbers, you always separate the letters and the numbers with a dash. So we put another dash. 2 dash ethyl. And then what's the name of the parent chain here?
Just cyclohexane.
Cyclohexane. So this becomes cyclohexane. Right? Letters and numbers are always separated by a dash. Numbers and other numbers are separated by a comma, right? So we have multiple, we put a comma in between them. We have multiple groups. Those numbers are always gonna separate from the letters by a dash. So at least they don't look as nasty as the coordination compounds, right? We have dashes and commas in there to kind of break things up for us a little bit. All right, so let's take 20-minute break before lab. Well, lab's pretty short today, so we'll probably finish up OChem in lab and then finish up the lab. In the lab, we get full credit as long as you're there smelling chemicals today.